It's recording. All right. So for this second part, we want to figure out the logic to find the maximum of two variables. Okay, the two variables, the input variables are x and y. In other words, you're given these two variables. They have specific values. How do you use logic to find out, how I should update z so that z becomes the maximum of these two variables? Any ideas?
Check to see which one is greater.
Okay.
X and Y.
Exactly. Okay. Very good. Check to see which one is greater, and whichever one is greater will get z to the same value. Okay. Very good. Now, since we don't know which one is bigger, we have to do a comparison. Okay. So if you want to look at this, I'll give this a try. If it doesn't work out, we'll just quickly switch back to the whiteboard because the finished product is already on Moodle in the class notes. So this is only being done so I can show you. I can show you the logic or how to design an algorithm like this step by step. So what we know now is we have a branch. Okay. If you look at this as a trail map, we know that sometimes we're coming in from the north. Okay, so this is the direction of the path. So we know that sometimes we have to go one way, and other times we have to go the other way. The only way you can make z the same as x is to use what type of statement? An assignment statement, right? Okay, and the assignment statements will go like z gets x. Okay. In other words, sometimes we know that we need the statement that we type here, which is x. Oh, that's too big, huh? Whoa, way too big. Yeah, 40 point is huge. Let's try 12. That seems too small. 16. Is that okay? Okay. Well, we already know what it is supposed to be anyway. So we know that sometimes we want to perform this operation. What is the other operation? If y turns out to be larger than x, then we want z to get updated to the value of y. The only construct that we have that can update the value of a variable is an assignment statement. So we know there's another assignment statement that we have to perform sometimes, not all the time. And then we'll take a look at that. So we say that sometimes we want z to get updated by the value of y. So we know that there are two alternatives that we have to consider. Sometimes we want x to be the source, and sometimes we want y to be the source. Okay. We also know that when you're done with either one, okay, so this is a step to perform. We know that when you're done with one of these steps, we have to merge these two paths. So let me just finish the picture here. Okay. So, oops. So we know that sometimes we want to go for the left-hand side, which is to update z with the value of x. Other times we want to go to the right-hand side to update z with the value of y. But in either case, doesn't matter which branch you go to, we still have to go out and exit this particular path using the same exit so that we can go to the next available statement to do whatever the next statement is going to do. The question now is, how do we decide that we want to go using this path or we want to go using the other path? How do we decide which way to go? Every time in programming, when you have a branch like this, where you start with one single path and then you end up with two alternative paths, you can only make that decision based on a condition. Okay? So remember, a condition in this class is a question. Okay, it's a question that can only be answered by one of two possible answers, true or false. So what we do now is we will use a rectangle here to represent a question. And we need to change the way it is filled. So we don't want any fill. We want the stroke to be solid like that. Okay. And we want some text inside it. Okay. What do you think is appropriate as a question inside this box?
Is x
greater than y.
Okay, very good. So we'll just say x is greater than y, and it is a question. Okay? Are there any questions at this point about this picture? I use a question mark here because this is a question. We are asking, is x greater than y? It can only have two possible answers. Now, how should I label these paths? How should I label the one to the left?
True. True.
Okay, very good. So if the answer to that question is true, we go to the left path. If the answer to that question is false, we go to the alternative path, the other side. Okay? Are you guys convinced that this logic, regardless of its pseudocode representation, will get the job done? I give you two variables, x and y, without telling you exactly the values, when I come up with the algorithm. Are you convinced that this algorithm will find the maximum between x and y and make z the maximum of the two? Yes?
Is there any way, could you make two statements, z has to be, if z has to be equal to or greater than x, and z has to be greater than or equal to y, then that would, but can you do that, or is this the only way to do this?
This is the easiest way to do it. This is correct already.
Okay.
This method is correct. And later on, when we talk about pre and post conditions, we will talk about a technique to prove that this actually finds the maximum between the two variables and makes z the maximum. Yes? Oh. Okay.
What would happen if x and y are the same number?
Oh, well, that's a good question. According to this picture, which path do you think will be taken when x and y are exactly the same? It will go to the right-hand side, the false branch, okay? But it will still be correct because if x equals 2 and y equals 2, the maximum is 2. So it will still be correct in that case. Because when x and y are exactly the same, you can pick either one, and it will still be the correct answer. So are we doing okay with this picture here? The next question is, okay, knowing that this is the logic that we want to express, how do we do it in pseudocode? That's the next question. And, of course, that is already answered in the notes. So getting back to my browser, where is my browser? Okay. And it's still processing the first half of the class. By the time we finish the second half of the class, the first half is already on YouTube, and you guys can watch it. Anyone with a smartphone can try to do it on a smartphone. You can actually read my notes, because it's just, plain HTML. It reads really, really well on a regular cell phone. And on YouTube, you can watch it on a cell phone too. So in other words, you can actually, review your material of this class, on your way here. But don't do it while you're driving, okay? If you're a passenger or you're taking a bus, that's good. But if you're driving, it's probably not advisable to read the notes and, watch the video clip at the same time. And the pseudocode representation is right here, okay? Let me see if I can put one next to the other one. I believe I can do that. Yes, very good. One of these days I have to bring a little setup into this classroom, because with that setup I can turn a Wii remote control into a whiteboard, inexpensive digital whiteboard. Okay, you guys can look it up. Just look up Wiimote, WIIMOTE, and then whiteboard. You will find how to convert your $25 Wiimote into an electronic whiteboard. Well, you have to make a little light pen first, but that's also just a few dollars at the most. Okay, so now we have the pictorial representation, kind of like a trail map, put next to the actual equivalent pseudocode. This pseudocode here, line 1 to line 5, represents exactly the same logic as this picture. Is that making any sense? If you just read it out in English, it kind of gives you the same idea. If x is greater than y, then z gets the value of x else z gets the value of y. I think it reads okay. Seems to, it seems to me, after 20 years of programming, that it makes sense. Okay, that's one thing about teaching this class is I can no longer undo what I have learned over the past 20 years. So what makes sense to me may not make sense to everybody else. So if it does not make sense to you, you have to let me know. Is that okay so far? I mean, is it kind of like following? This is the exact or almost the exact notation in VB. If you're writing a Visual Basic program to do exactly the same thing, all you have to do is to replace the left arrows with a single equal symbol, and it becomes a VB program. Are there any questions about this part here? The next question is, I can understand and remember the trail map, but I can't make an association with the syntax of the pseudocode. What should I do? Other than studying and just review the material, I really don't know what else can be done. I mean, it really is just an exposure kind of thing. You just have to read it, look at the picture, read it, look at the picture, and eventually, I think you will get it. Yep.
So you have to be careful, like if you're programming this, you'd have to be careful to list the false state or the true statement first.
Correct.
Right?
Yes.
Because if you didn't, then you're going to get the opposite results.
Yes, the order is very important. In other words, the statement or the statements in some cases between the then and the else, that's what you want to do when the condition is true. The statement or the statements between the else and the and if is what you want to do when the condition is false. Okay? Very good. That's a good point. When you have annoying languages like Perl, they give you, in addition to if, they give you unless. which just throws a big whole confusing thing into the whole programming thing, because unless is like if, except the polarity of the logic is flipped. Okay, so I'm not going to touch that in this class. In this class, we only use if, which is common to all programming languages. Okay, let's go ahead and trace this algorithm and play with a few test cases. Okay, because that's the best way of looking at or the best way to start to understand the pseudocode for something like this. So once again, we go back to OpenOffice, and I'm not sure. Do you guys want me to save this one? That's kind of trivial. You want to save it? We'll go ahead and save it. When I save documents for a class like this, I would use one folder for one day, and at the end of the class, if someone reminds me, I will upload a zip file of that entire folder up to Moodle, so then you will get the same documents, all the same documents that I worked on during the class. But somebody has to remind me to do it at the end of the class. Reminding me right now does not help. Okay, why? It doesn't let me create a new folder. Odd. That's okay. I can always use the command line to do it. 2011-0128 cisp300. And with that, I can save it. I'll call the first one assignment statements, because that's all it does. And now we can close this and open a new one. The new one is basically the same code that we were looking at a little bit earlier. If x is greater than y, the parentheses are optional in this class, but in C they are not optional. In this class, if you just say if x is greater than y without the parentheses, that's fine, it's not a problem. But with extra parentheses, I think it is more clear which part is the condition. That part is completely subjective. Z gets the value of x, else z gets the value of y, and if. And then we have the line numbers, just like that. And these two have to be indented. I will also talk about indentation later on, the importance of indentation. And now we can use a different window to trace it. Okay, let's go for 3 cases, 3 test cases. In the first test case, now that we have conditions, we need 1 column for comments. I'll show you why, how we use this particular column. And we still have the same thing as before, a line number column, a column for x, a column for y, and a column for z. X and y, in this case, I have to have some known values for x and y, because there's no way I can compare x and y if I don't know the values of these variables. So I have to be very specific in this case, and I can say x equals 2, y equals 3 as an example, and z is going to be updated by this code, so it doesn't have to start with a specific value. Are there any questions about this part of the setup? I can no longer say that I don't know anything about x or y, because if I did that, I would not know how to compare the 2 variables on line 1. Okay, let's go to line 1. If you look at line 1 of this pseudocode, do you think x will be changed?
No.
Do you think y will be changed? Or z?
No.
Nothing gets changed, because when you evaluate a comparison, it is only reading the value of the variables. It is not changing the value of any variable. So in this case, I know x, y, or z, they're all unchanged by line 1. And I will switch to a shorthand mode at this point, where if the value of a variable does not change, I do not write anything. So I'll leave it blank to indicate that, nope, I'm not making any changes to any of the variables. But instead of doing that, I have to leave some comments, because now on line 1, I have to say x is greater than y is evaluated to, is it true or is it false? It is false. Okay, very good. Where do I go next if the condition is false?
To line 4, yeah.
We go to line 4. Very good. Now, if you say we go to line 3, I won't take any points off, but we don't trace the else line, because that line really does not do anything. It is what I call a marker line. A marker line is really just a bookmark to say this is the beginning of the else part. But other than that, it really serves no purpose, and as a result, when we trace the algorithm, we don't trace line 3. What do we do on line 4? We change z to become the same as y, and y has a value of 3. As a result, z also ends up with a value of 3. After line 4, what do? We don't have anything else to do. So we just say post, and so the post condition is x ends up with a value of 2, y ends up with a value of 3, and z also ends up with a value of 3. That's the outcome of this algorithm. Are there any questions about this trace, this particular test case? Okay. Is it correct? Did the algorithm do the right thing? Seems so. Okay. Are we sure the algorithm will be correct in the next test case? No, not until we actually test it. Okay, so we'll go ahead and do the same thing. I'm going to set up the same columns. And this time I will use 3 in x, 2 in y, unknown in z as my precondition. And to shrink or to make the columns as narrow as it can, you can select the columns first, and then you double click when your mouse over changes to this double arrow symbol. When you double click it, it will resize the columns so they look nice. They're basically as narrow as they can be and still be reasonable. Okay, we go to line 1, and same thing. We have to indicate the result of the comparison. Is it true or is it false? It is true. X is 3, y is 2, 3 is greater than 2. Then where do we go?
Line 2.
We go to line 2. Line 2 does what? Z gets the value of x. Since x has a value of 3, z ends up with a value of 3. And then where do we go next? well, line 5 is okay, but we just go to post right away because line 5 is just a marker at the end of a conditional statement. Yes?
So we don't need to put any values in the post?
No, because there's the same.
So what's the point of having the post?
You tell me that you're done when you write post. Now, at this point, it doesn't seem that important because it is quite clear there's nothing after this. But when we have loops and stuff like that, then it becomes very important because you're telling me, okay, we are done with the very last iteration of the loop. Okay, so post is the same as QED in mathematics. When you prove, when you have a math proof, you have to use QED to indicate this is the end of the entire proof. It's basically the same thing. Okay, so is that the right thing to do? Did the algorithm work correctly if its purpose is to find the maximum and put it into Z? Seems to work. Okay, so we have one more test case to go. And then I'll ask you a question, and you can tell me what you think of it. We have a precondition here. This time we'll try 2 and 2 and put a question mark into Z. Here we have line 1. Line 1 is still doing the same comparison. You tell me the answer.
False.
Okay, it is false, and as a result we go to line 4. Line 4 is going to copy the value of y to z. Z ends up with the same value of y, which is 2, and we are done. Is that the right behavior? It's still finding the maximum of x and y.
Did you do line 2 also?
Hmm? No, because the code does not say so.
Okay.
Because the program says, if x is greater than y, and only if x is in fact greater than y, should I execute line 2. And that's why, in this case, even though if you executed line 2, it would have given you the same result, you do not go to line 2. Because we are modeling, we are tracing the program as if it is executed by a computer. And the computer will not go to line 2 in this case. Okay? All right. Are you convinced that the algorithm is correct? Kind of. Okay. How do you know for sure that if x is 53 and y is 16, that it will do the right thing?
You have to run it.
You have to run it. So how many test cases like this do I have to go through to be really, really confident that the algorithm is correct? Infinite, because there's an infinite number of x and an infinite number of y. Okay, so that means the way we have been doing it like this, to feed it different test cases, can give you a good feeling that the algorithm does work in some cases. But that's basically all that you can be, or you should be convinced of, is it does work with these 3 cases. Okay. Because in the next test case, it may not work. Now, this is a really, really simple algorithm too. Okay? So when you're writing something as complicated as Windows 7 or Linux as operating systems, how do you know the operating system is going to work correctly?
With Windows, you know it won't work correctly.
It will work correctly most of the time. Yes. Okay. Okay. This is program or software verification. How do you know for sure the program or the software or the algorithm will do the right thing all the time? That's a big question.
You never know, I guess.
Well, at this point, we have test cases to give us a general feel that, okay, I'm fairly convinced that the algorithm will do the right thing. But to prove that the algorithm will always be correct is a topic that we will visit, but not today. When we get to pre and post conditions, we will look at the same algorithm like this again. But in that case, in that week, we will prove that this algorithm is correct regardless of the values of x and y. In other words, you can throw any x and y to this algorithm, it will still be correct, and I can prove it. Okay? So when we get to that point, we will prove the correctness of an algorithm. Simple ones, not complicated ones, but I do want to introduce the concept of proving an algorithm is correct in that case. But at this point, we just have a pretty good feeling that it is right, but we are not convinced that it has to be right all the time. So I'll go ahead and save this one too. into today's folder. And I'll call this max2 because it finds the maximum of 2 variables. So getting back to the notes here, it has full explanation of what a conditional statement is. If you read through this whole thing, it should tell you exactly the same thing that I just went through today. And guess what? It has the same trail map that we saw a little bit earlier. Now, let's go ahead and take a look at what if we want to find the maximum of 3 variables, w, x, and y, and put the maximum into variable z. In other words, I'm just extending the logic of the program, the pseudocode that I wrote a little bit earlier, to handle not 2, but 3 variables. Okay? I'm coming up with a framework like this, and then we'll talk about what we need for C1 and C2 in order for this framework to work correctly. This framework is assuming that there's a way for me to confirm that W is in fact the maximum of the 3. Okay, C1 is a condition that I don't know how to quite express yet. But C1 is saying that if C1 is true, I know W is the maximum. Well, what if W is not the maximum? Well, we'll check condition 2 in that case. If condition is true, then we know X is the maximum. As a result, I can use X to update Z. If C1 is not true, which means W is not the maximum, and C2 is not true, which means X is not the maximum, what do I know for sure, since I only have 3 variables? Y has to be the maximum. So in the last case, I don't need a condition because this has to be the case, because if C1 is false and C2 is false, then I know Y is the maximum, and I can just update Z with the value of Y. So now my next problem is how do I express the condition C1 so that I can, in one single condition, I can confirm that W is the maximum of the 3 variables. That's the question. I cannot use a single comparison anymore. Because in one single comparison, I can only establish the relationship between 2 variables. I have 3 variables now. I need 2 conditions. Now, when you have 2 conditions, you have to somehow relate the result of the first comparison with the result of the second comparison and come up with a single answer. And what we need is a logical operator. And we'll come back to this a little bit later, and instead of completing that algorithm at this point, we'll talk about conjunction. Conjunction is the word and in English. Okay, we have all used this word, and hopefully we have all used it in the correct context. Are there any questions of how to use the word and in English? What does it mean when we use the word and, especially when we're talking about logical stuff?
Also as well. Also.
Also? And believe it or not, the English word but, B-U-T, also means conjunction. Okay? The word but, is a contrasting conjunction, which means, the first part may indicate something that is positive, the second part may indicate something that is negative, but they are both true. Okay? So when we use a conjunction, the conjunction itself is true if and only if both sides are true. Okay? I can give you a few examples. Today is a little bit cold and sunny. Is that a true statement? No, it's not sunny out there. Okay? Even though it's kind of cold, it's not sunny. How about... Okay, I can give you guys a trick question. This class is beneficial, but yet boring. Okay? Now, how can I make that statement true? Okay? The question is not whether it is true, but how can I make it true? I can make it true if and only if you guys graduating from this class will actually get the necessary knowledge to move on to cisp300, and yet all of you get bored completely in the class. That is the only way to make that statement true. If any one of you feels that this class is not boring, you think, oh, this is kind of cool, that statement is false already. Okay? So that brings us to the definition of and or conjunction. Most of us know this already. It's just that we usually do not spell it out like this. True and true. Okay, let me just kind of go back here a little bit. In English, conjunction is the word and. The mathematical symbol is kind of like a TP, like an inverted V. In C and C-derived languages, the operator is the ampersand or double ampersand operator. In Pascal, SQL, Visual Basic, PHP, Python, and so on, it is just spelled out as A-N-D. Now, when you move on to cisp300, this particularly applies to people who are moving on to C. There are two operators that are kind of similar but not the same. There's the double ampersand operator, which means logical AND. There's also another operator, a single ampersand, which means bitwise AND. Okay? Wherever a double ampersand can go, the single ampersand can go in terms of syntax, but they are not exactly the same thing. If you use the wrong one, your program may work most of the time. That's the worst thing. If it doesn't work at all, it's good, because you can catch it early on. Unfortunately, the differences between ampersand and double ampersand is so subtle that it might work all the time with one compiler, and yet it does not work when you compile the program with another compiler. So that means when you move on to C, pay attention to the logical AND operator, because I guarantee someone is going to get bitten by this one. Because I have been bitten by this one many times. Okay, the definition of ampersand is true and true is true, false and true is false, true and false is false, false and false is false. That's the definition of the conjunction operator, the AND operator. Is that okay so far? Does that remind you of one of the arithmetic operators that we know? Multiplication. Multiplication, okay? It kind of resembles multiplication, where true is 1 and false is 0. 1 times 1 is 1. 0 times 1 is 0. 1 times 0 is 0. 0 times 0 is 0. Okay, so if you want to make an association, to something that you already know, you can look at this as multiplication. False is 0, and true is 1. Okay. The next slide talks about disjunction, which is also a fancy word for the English word or. Now this one you have to be extra careful, because in English we have or, and then we also have either or. Okay? Disjunction is a simple or. It is not either or. This operator also requires two sides. The entire disjunction expression is true if and only if at least one side is true. Okay? The mathematical symbol is a V symbol. In C and C++, the disjunction operator is a double bar symbol. And once again, guess what? There's an operator that is a single bar. And guess what? That single bar operator is related to a double bar, but it's not exactly the same thing. And wherever a double bar can go, a single bar can go, syntactically speaking, even though it does not mean exactly the same thing. So if you accidentally use a single bar instead of a double bar, your program may behave as if it is working correctly, but it is in fact not entirely correct. So be very careful with the double ampersand and also the double bar when you move on to C. In most other languages like Pascal, SQL, Visual Basic, and so on, this is just simply spelled out as or. The definition of or is quite simple. True or true is true. False or true is true. True or false is true. The only time it is false is when you have false on both sides of the operator. Okay. Any questions? No questions? Okay. I think this is a repetition of stuff that you normally know already. It is just a formal, definition of what we already know for the most part. The last one is negation. Negation is the English word not. Whenever we use the word not, we are negating the meaning of some logic. This operator only has one side, only one value to work on. The negation expression is true only if and only if the value of the right-hand side is false. The mathematical symbol is a cliff symbol. It's a horizontal bar followed by a drop. In C and other C-derived languages, the operator is the exclamation point operator. In Pascal, SQL, and Visual Basic, it is just spelled out as NOT not, which is easier. The two possible combinations, if I want to define negation, is not true is false, and not false is true. Okay. Are there any questions about negation? Yep.
Why would you say not true? Why wouldn't you just say false?
Because sometimes this is not just true as a constant. This is a whole big expression. So if you have a big expression, conjunction, disjunction, or whatever, and you put a negation before that, then it will just turn. If that expression gives you true, then the end result will be false because you're negating the whole thing.
Oh.
So this is just a definition of what negation can do. Is if you negate a true, it becomes false. If you negate false, it becomes true. Okay. Are there any questions at this point about the operators? Now let us go through an exercise to make sure that we do understand the operators. So we'll go ahead and do this exercise using my text editor here. And the exercise is like this. You don't have to turn in anything. I'm just going to have you guys to think about it, and I'll talk about the answer. If the only comparison operator is greater than, and you can use any of the logical operators, how do we define all other comparison operators? That's the question. In other words, I give you a weird programming language in which the only thing you can do to compare something is greater than. That's the only thing you can do. You can check whether x is greater than y. You can check whether z is greater than x, and so on. But you don't have any of the other comparison operators. You don't have less than, you don't have greater than or equal to, you don't have less than or equal to, you don't have not equal to, and you don't have equal to. But I also give you all the other logical operators. I give you not, I give you or, I give you and. Can we do this? Can we express all the other comparison operators using only greater than and also the logical operators that we have talked about? And also changing the order of the operands and stuff like that. Let's go ahead and take a look. Okay, greater than is trivial. Okay, x is greater than y is equivalent to x is greater than y. Okay, that kind of goes without saying. What about x is less than y? How do we express x is less than y when you can only have a comparison for greater than?
Y is greater than x.
Yep, we just flip the order. That's easy. That's good. How about x is greater than or equal to y? And you can only do greater than. What about this? Let's just think about this. Okay, we'll just think about it a little bit. What I want to do is to express x is greater than or equal to y. X is at least as much as y. But I can only use greater than to express everything. Do you think this is doing the same thing? It is not the case that y is greater than x. If I tell you that y is not greater than x, doesn't it mean the same thing that y is less than or equal to x? Which means x is greater than or equal to y? Okay? Are we convinced of this? Okay. Okay, so what about the other one? That's the other one. That's easy, right? X is less than or equal to y. Yeah, we just flip the order of the comparison, and we're done with it. What about x is not the same as y? Well, there's a reason why not equal to is less than greater than, because it is the same as less than or greater than. So the equivalence is going to be what?
Y is greater than x, or x is greater than y.
Yep, that's it. Very good. And the last one is x equals to y. How do we express x equals to y when you only have greater than?
Not x is greater than y, and not
Okay.
x.
There are several ways to do it. One way is just to negate the previous one, because not equal to is equal to. But that's a little bit difficult to understand. So what we can do is to apply De Morgan's law. De Morgan's law is saying that the previous form is the same as saying not x is greater than y and not y is greater than x.
Why did you put 2 sets of parentheses around it?
Because one is in the wrong place. That's why. Okay, that's the correct way. Is that making any sense to you? Okay. So this is a nice little exercise because it is all we are doing is we're going back to all the comparison operators that we already know. We're going back to the logical operators that we already know, and we're just saying, okay, how do we use combinations of those weird things in a weird way so that we can express all the comparison operators given only greater than. Are there any questions about this little exercise here? No questions? This is all good? Okay. Now obviously, I don't have to kind of talk about this, but double negation is positive. Okay? When you say the negation of something, you get that something back. Okay, that's very important because you can simplify equations or you can simplify expressions like that by saying, oh, the negation of something is just the original thing. If there are no questions, we will go back to our example and finish up the logic to find the maximum of 3 variables. So going back to the example. This is the proper logic. Okay, let's just take a look at this and see if it makes any sense. The first part says if w is greater than or equal to x and w is greater than or equal to y, do you think if this highlighted part is true, it confirms that w is the maximum of the 3? No? Yes?
Yes.
Okay. So in that case, if this is true, I can go ahead and execute this statement, and I'm done because w is the maximum of the 3. If this is not true, then I have 2 more choices to pick from. This is actually a little bit more than it has to be, but it is not incorrect either. So if w is not the maximum, I will try x to see if x is the maximum. If x is greater than or equal to w and x is greater than or equal to y, that will confirm that x is the maximum of the 3 variables. In that case, I use x to update z.
So when you say this is wordy, essentially you wouldn't have to compare x and w because you
Correct.
previously compared x and w.
Yep, that is correct. And the last case is y, because if I can confirm that w is not a maximum and x is not a maximum, guess what? Y has to be the maximum. And this is what I call a multi-branch conditional statement, because instead of just having if, a condition, then, and then else, and then and if, I now have 2 conditions to evaluate. If this is false, I will have a second chance to evaluate this one. Are we doing okay so far with the general logic of this?
I must have missed something. What's that character in the middle?
The TP?
Yeah.
That's and, that's the conjunction.
Okay.
Yeah, that's the mathematical symbol for conjunction. Are we doing okay so far with this logic? Okay. And this is the trace, when W, X, and Y are all 2, that's the trace for that case. And the next one, the next picture talks about, else if. In other words, if I have to draw a picture, this is actually the wrong picture because you can see that the conditions are not correct. But if I have to draw a picture, this is what it looks like. Or if I try to use the other program to draw the picture, let me see if I can find that. Let me go ahead and save this one first, and then I'll draw another picture. Let's see, we want letter size. Okay, so I'm going to draw a picture to represent the logic of the previous slide. So I want to make a picture to represent exactly this logic here. So we come in here and we have a branch. Because if you look at this code here, the first condition is like this. When you read pseudocode, remember, you're always reading pseudocode from top to bottom. You don't change the order. You don't evaluate the second condition before the first one. You always evaluate from top to bottom. So that's why when we try to express this logic in a graphical form, the first question to ask is whether W is greater than X and W is greater than, whether W is greater than or equal to X and W is greater than or equal to Y. So that means if I want to draw a box to represent the question that I'm asking, it is going to be W is greater than or equal to X and W is greater than or equal to Y. That is the first question that I ask. Are there any questions about this part? No questions? Then we can go ahead and label the branches. When it is true, we go this way. When it is false, we go the other way. When it is true, there's only one thing for me to do, which is to update the value of Z with the value of W. Are we doing okay so far? Okay. Now, if W is greater than or equal to X and W is greater than or equal to Y evaluates to false for any reason, I now have a second condition to evaluate. In other words, I am going to extend the picture a little bit here, and we have a second branch. Every time you have a branch, you have to have a question to ask. So that means if I'm going to ask the second question, what would that be? What would be the second question?
Is X greater than or equal to?
So we say X is greater than or equal to W, and X is greater than or equal to Y. And once again, there are two possible outcomes. The answer to this question is either true or false. If the answer is true, we go to this branch. If the answer is false, we go to the other branch. The true branch here is going to say Z gets updated by the value of X. The false branch will instead say Z gets the value of Y. Are we doing okay so far with this? So if I want to finish this whole picture, just drawing the bubbles around the actions. Okay.
So once you can limit it down to two choices. So that's the goal. So no matter how many you have to knock off one, and then another, and then another.
Yep. But the three paths, they all merge in the end. That is also very important. Like that. That's the pictorial representation of the pseudocode that is in here. Are we doing okay? Are we making the association between the pseudocode representation and the graphical representation? Okay. Let me save this first. Is my drawing doing okay? I mean, is it not too bad?
Not too bad.
Not too bad. I could do it, better, with the actual whiteboard. But if I do it on the whiteboard, then I cannot save it as a file. If I do it like this, then I can actually save it as a file. Okay, so this seems to be pretty easy, right? Let's go ahead and think about something, or use another example to illustrate, the concept of multi-branch conditional statement. I call this multi-branch conditional statement because there's one branch here and there's another branch here. And guess what? You can keep using else if and have more branches here, more branches here, more branches here, and keep going like that. Now, it is very tempting a lot of times to use constructs like this because it seems like it's a very handy way to say, oh, I have multiple things to test, and this is a quick and easy way to see which of these many conditions is true. So what I want to do next is to give you an example where funny things will happen. Okay, so here is a new pseudocode using concepts that's just like that, and we'll say if x is greater than say 30, then we'll do something. Okay, I don't know why I want to change z to 1, but that's what I'll do. Else if x is greater than say 15, then z gets a value of 2. Else if x is less than 20, then z gets a value of 3. Else if x is, I don't know, greater than 0, then z gets a value of 4. Else z gets a value of 5, and if. Okay. So this is a, it's a very tedious program, has a lot of branches. That's my pseudocode. Trust me, tracing this is a whole lot easier than writing the actual code. Now we will trace this code. We trace this code with certain assumptions about x. Because we have a condition, we have conditions to evaluate, you will need a column for comments so that you can tell me why you make decisions that you do when you trace the algorithm. We also need to know the line number and also the value of x. The precondition, there's also z, don't forget z. Let's say in the first case, the precondition is, let's go for a really, really easy one. X starts with a value of 200, and z starts with some unknown value. That's my precondition. Before line 1, this is what I know. What is the result of line 1? First of all, don't you see a little bit of a problem here? Because I can see 3 conditions being true at the same time. So which one should I pick? The very first one. You don't get to choose. Okay, this is not a choice. Because when we evaluate an algorithm like this, we always evaluate from top to bottom. Okay? In other words, don't even mind this condition. Don't even mind this condition because you have to focus on the very first one first. Is that okay? And if you look at the picture that we have drawn so far, you can see the same thing. Basically, this is the condition that you have to ask first. Okay? And you have to act on the answer of the first question before you do anything else. So that's why this program may look confusing, but it is really not confusing because you do not get to choose which condition that you want to evaluate. You always go from the first one in the program. In this case, x is greater than 30 is true because x is 200. So which line should I go next? We go to line 2, z gets a value of 1, and then where do we go?
Post.
We are done. Okay? Now this part is extremely important because when we look at this program here, we'll see, oh, but wait, x is also greater than 15. Don't we need to go to line 4? And x is also greater than 0. Don't we need to go to line 8? The answer is no, we do not. Okay? Because you have to look at this and think about the picture of this code, and you will see that, oh, once we make this branch and assign a value of 1 into z, we go all the way out to the end of the entire statement. Is that okay? Is that clear? Okay. So you just have to kind of flip between the text representation and the graphical representation, because in this case it is not the same program. But in this case, once we know that w is greater than or equal to x and w is greater than or equal to y, we go for the true branch, we copy the value of w into z, and then what? We go all the way out. Okay? Is that okay so far? Okay. This is a very, very important point, because I can give you some additional test cases that will show you, this program, has very strange behavior sometimes. Okay, the second test case, comments, line number, x and z. Z always starts with some unknown value, because whatever it starts with, I will overwrite it anyway, so it doesn't matter what it starts off with. In this case, let's say x starts with a value of, let's make one that is somewhat confusing, but I don't think you guys will get confused by that anymore. And this is my precondition. Okay. Hey, how come they don't all get shrunk? There we go. All right. So we go to line 1. Line 1 is evaluating x is greater than 30, and that is false. So where do we go next?
Line 3.
We go to line 3. Line 3 is checking x is greater than 15. It is false. Then where do we go? Go to line 5, x is less than 20. It is true. So z gets a value of, so we go to line 6, z gets a value of 3, and we are done. Are we doing okay so far with this? Okay. Let's try a few more cases. Precondition, this time we can try, -5, okay? X starts with a value of -5. On line 1, x is greater than 30 is false. We go to line 3, x is greater than 15 is false. We go to line 5, x is less than 20 is true. And so we go to line 6. Line 6 is going to make z equal to 3, and then we are done. That is kind of odd. Is there any way I can go to line 10 and make z update to 5?
No, and you can never go to line 7 either.
Aha! So there are what we call dead branches here. Okay? These are called dead branches because there's no way we will actually go to those branches regardless of the value of x. There's no way you can pick a value of x so that we can end up on line 8. Okay? The same thing goes for line 9. Okay? Well, that means, with a program like this, even though it seems like that sometimes z may get a value of 4 and z may get a value of 5, that may never happen. Now, if I want to create more dead branches, it's easy. Okay? All I have to do is to flip the order of this condition, and now I can create more dead branches. Because anything that is greater than 0 will be caught by the first case once I swap the condition. So it is pointless to compare to 15 and 30 anymore, because x greater than 0 will cover those cases as well. Are we doing okay so far with the concept of dead branches? Okay. Now, why would someone write a program like this? Well, remember, this is a very simple case just for the illustration of the problems of a multi-branch conditional statement, or potential problems of a multi-branch conditional statement. Let's say you're writing a program for, say, TurboTax, okay? And when you report taxes, there are a lot of rules that can apply, but you need a big long combination for conditions to be true in order for that rule to apply. So it makes sense that in TurboTax there may be constructs like a multi-branch conditional statement, just like this, except it applies different rules to different people depending on whether they qualify for something or not. What if you specify the conditions in a way that one condition or two conditions of the multi-branch conditional statement can be true at the same time? Then the order of those conditions become important. Okay, whatever comes first will be the first one that fires, and then the second one will never get a chance to fire. So that's why when you specify anything like this, you have to kind of think about, okay, is it possible for more than one of these things to be true at the same time? And when it does, which one will fire? Okay, it is very important. So now that this is fresh in our minds, we'll go ahead and talk about your next homework assignment. Okay, this is a weekly class, and we have to have weekly assignments as a result. So I'll call this bad multi-branch. Okay, because the code seems to suggest that Z can get updated to 4 and 5, but in reality, those branches are dead. You can never get to those branches. Your next homework assignment has something kind of similar to this. And if you log into Moodle and just look at upcoming events, you will see multi-branch as your new homework assignment that is due on the 4th of February, which is next Friday, right before the class. So we'll go ahead and click on that, and it has, this is basically the general format of all your homework assignment, as well as your examination questions. So you download this document, the algorithm is in sheet 1, trace it based on the precondition as specified in the other 3 sheets in the document. Make sure that you use OpenOffice to work on this document and submit your finished document using the upload interface. We'll just take a quick look at the algorithm itself. Goes all the way back to sheet 1 to look at the algorithm itself. And this is the algorithm. Okay? If x is different from y, then z gets 1. If z is greater than y, x is greater than y, z gets a value of 2. Else, if x equals to y, you get a different value into z. And if everything is false, then you have put 4 into z. And these are the preconditions that you have to handle, and that's it. I don't think this will take too much time, but it is a good reinforcement of the concepts that we have talked about up to this point. Are there any questions about this homework assignment? No questions? Okay. Very good. And so we are almost done with this module as well. The language issue here, you can read it if you want to. It basically applies to C, people who are moving on to C and C++, but I will not ask any questions about this part here, so it is completely optional. If you want to read it, that's good. If you don't want to read it at this point and wait until CISP 360, that's fine with me as well. Now we are going to move on to another module. The next module is loops. Okay, so finally, now we have a way to make decisions. The first module, variables, expressions, and sequences, will give us only a mechanism to change variables, assignment statements, basically. And you can have sequences of those things, but you cannot make decisions. You cannot say, sometimes I want to do this, and other times I want to do that. You don't have a decision-making ability. And conditional statements will add to that. Okay, conditional statements allow your program to make decisions. Okay, here's a condition based on the result of evaluating a condition. Sometimes I go this way, sometimes I go the other way, and now your program is smarter because it can choose between 2 different paths. And when you have multi-branch conditional statements, then you have additional branches, and you can pick any of those depending on the conditions. But we cannot do something over and over again. Why would I want to do something over and over again in a program? Well, tell me something that you do over and over again in daily life. Eating food with, yeah, that's the example that I used in the notes. What about parking on Tuesday at 10 a.m.? You have to drive around the parking lot, make a round. I don't find an empty spot, and then what do? Do it again, right? Until what? Until it times out, it's like, oh, half the class is already over. I might as well just go home now. Okay? So there are loops in daily life. We do things in a repetitive fashion. Many things that we do is repetitive. Doing dishes, washing dishes, that's a repetitive process, right? You pick up one, dirty dish, you wash it, you put it on the other side. What do you do next? You pick up the next one. You do the same thing. You pick up the next one. You do the same thing. And how do you stop that process?
Until they're all clean.
Until you don't have any dirty dishes anymore. Okay? So we do have to handle loops. Yep, go ahead.
Before you get tired.
Before you get tired. Yep. And that's why some people use paper plates. I know a couple, back in Davis, I know a couple who use paper plates and paper cups every day for everything. They never do dishes, ever. And because they live in an apartment, there's no such thing as, the trash can won't hold all the trash, because they have big dumpsters in apartment buildings. Not very environmental, I'm afraid.
You're saving water.
You're
Saving water.
Yep, you're saving water, but you're wasting landfill. Yeah, I think they're both expensive. They will all get very, very expensive. So all I'm saying is loops are also very important when you write algorithms, because many, many times we have to be able to specify, I want to do that again until a certain condition is either true or false. So let's go ahead and take a look at loops at this point. And obviously the title is a play of the words, because what is a loop again? Because the word again implies what? A loop. Very good. A loop is a control structure that permits certain steps in a program to be repeated or to be done again. Without loops, programs cannot perform certain steps over and over again, and often without knowing exactly the number of times to repeat to do something. And in real life, we also rely on loops, in terms of logic. The logic of eating is repetitive. You basically keep, eating a spoonful of something until you're no longer hungry. And repeat that again, because we are going to talk about what I call a post-checking loop, so that we can do something over and over again. And instead of just looking at the pseudocode at this point, let's look at the logic of a post-checking loop first. And the picture of that is a little bit different from the pictures that we have seen up to this point. This is the logic or the picture of a post-checking loop. Let's see here. Now we have a bit of a problem now, because I have to clearly indicate the direction of the paths. Every path that we use to specify an algorithm, they're all unidirectional. In other words, they are all one-way streets. So I have to be very clear to say that when you're coming in, this is a one-way street, and this path here is also a one-way street. You can only go from this point back to this point here, but when you're here, you cannot take this path in a reverse direction. Are we okay with that? All these streets are one-way streets, like most of the streets in San Francisco. And they change the direction, from time to time too. Like this street used to be like this one way, and they would change it to the opposite way, at a later time. That makes navigation a little bit interesting in San Francisco, especially when you're going uphill like this and driving a stick shift, and there are pedestrians, crossing the road everywhere, crossing the street everywhere. Now, so according to this logic here, you don't have a choice. You have to take a bite. You have to take the first bite. Because I don't see any way to avoid this step here, do you? This is a one-way street coming in. This is a one-way street only going into here. So you don't have a choice but to take a bite first. Now, after you have taken the first bite, you get to this place here. This place is a branch because you have one way to come in, but you have two ways to get out of the branch. And every time you have a branch, you have to expect a question, because that's the only way you can decide which way to go. In this case, the question is that person full? Is that person not feeling hungry anymore? If the answer is true, that person is feeling full, then you can just go for the true branch and get out of the loop. If the answer is false, then that person will have to follow this path here, go all the way back to the beginning, take another bite, get down to this junction again, ask the question one more time, and then decide which way to go. Are there any questions about this logic? Yes?
So this works unless you run out of food.
Well, there's no testing for running out of food. So you will take another bite, except that bite has no food. At that point, it becomes an infinite loop because that person will keep feeling hungry because you're taking a bite of nothing. So eventually, the person will die, and then then you exit the loop. Then the program terminates. Yes. Let's just call it pulling the plug on the computer. Right, so let's go ahead and look at the text representation of this logic, because this is the pictorial version, and the text representation is like this. Repeat, take a bite until one is full. This part here is a condition. This part here is an action to take. So the best way to gain a better understanding of this is to trace an algorithm that has a loop. So that's exactly what we'll do next. So once again, I'll use the spreadsheet to give us an example and a trace. And we don't need anything that is really, really complicated. We can just go for a relatively simple case. Repeat x gets x plus 1 until x is greater than 3, let's say. So that's a fairly easy program to trace. And I intentionally do not have any initialization before the repeat loop. So this way I can also set up multiple test cases and start with different values of x. In the first test case, we'll start with a very simple one. In the first test case, we have one column for comments because we have conditions to evaluate. We have line number so that we can tell, x has this value after this line. And then we have x as a column because we want to keep track of the value of x. Let's just say that before line 1, with this particular test case, I know that x has a value of 0 to begin with. Don't ask me why, because somebody just told me, tag, assume x has a value of 0 before line 1. That's basically what this means. Now I'm ready to run the program. I don't trace line 1 because line 1 is repeat. It is a marker to indicate the beginning of the loop. Okay, so I don't trace line 1. If you write down line 1 in a trace like this, I won't take any points off. I'm just saying that it is not very helpful to trace line 1. So instead, I will start with line 2. Line 2 is an assignment statement. We evaluate the right-hand side first. X currently has a value of 0. 0 plus 1 is 1. And this entire expression, or the value of this entire expression, is used to update x itself. So x is now updated to a value of 1. Then I go to line 3. Line 3 is not just a marker. It also has something to do because I have to evaluate the comparison. X is greater than 3 is false. So what do I do next? We go back to line 2. We go back to line 2. X already has a value of 1. 1 plus 1 is 2, so x is now updated to a value of 2. We go back to line 3, and we ask the same question, ending up with the same answer. 2 is greater than 3 is false. We go back to line 2 again. This time we increment x from 2 to 3. We go back to line 3. X is greater than 3 is, it's still false because 3 is not greater than 3. We go back to line 2. X is now incremented to 4. We go back to line 3 and evaluate the condition. This time 4 is greater than 3, so the Boolean expression is true, and we're done. This is why it is important to indicate post, because let's say we have a test, okay, and this is a question, and I have to determine whether you really know this is the end of the algorithm, or whether you are not done yet and you somehow do not know how to terminate the program. So that's why post is important, because without a post, I don't know whether you are done or not. So the post is very important to indicate, yes, I am done tracing the algorithm, and the post condition in this case is that x ends up with a value of 4. Any questions at this point?
So if we're taking a test and we can trace the algorithm maybe 2/3 of the way and then we can't figure it out, you just want us to leave it blank?
Yes, just leave it blank, and I will give you partial credit depending on what you have answered up to that point. Mm-hmm. I try to assign partial credit, in tests like this, because your test questions will be kind of like mini homework assignments. So all of the test questions are traces, kind of like this, and sometimes people make like careless mistakes, like in the calculation, forgetting to add 1 or subtract 1. So that will impact everything else. But assuming that the rest of the program or the rest of the trace is consistent with that mistake, I will only deduct points once, because the rest of the program is wrong because of that one little step. So as long as I can still find indications that that student understands the concepts that I'm looking for, that student will still get partial credit for the demonstration of the understanding of the concepts that I'm looking for. But the mistake itself will still cost some points, because compared to a student who did not make a mistake, obviously one student should get a little bit more points than the other. Okay. Let's take a look at sheet 3. We'll have another test case here. Comments, line number x. This time, let's say in the precondition, x has a value of 20 to begin with. Now this is also getting back to the point of, you don't want to, okay, how should I put this? As people, we have the ability to eyeball things. Okay, I call it the eyeball algorithm. We read multiple lines, we read multiple things at once. That's one of the best things that we can do. That's how we can read the newspaper and whatnot really, really quickly. But it can also work against us when we try to learn algorithms. Because when you look at a precondition like this and you look at the code like this, you go like, oh, so we don't even have to bother to get into the loop, because we are going to get out anyway when x is greater than 3. But that would be incorrect. That would be incorrect, because you have to do it the same way as the computer would have done it when this program is run by a computer. So that means you still have to read the program line by line and determine what to do on a line-by-line basis. In this case, we still start with line 2. Now we are still starting with line 2 because, oops, not the right picture. Because the picture looks like this. Every time you have a repeat until loop, which is also called a post-checking loop, because we are checking after the action, you come in here, you don't have a choice, you have to perform the action at least once. So that's why when we trace this algorithm, we have to follow exactly the same rules. We have to go to line 2 first, which bumps the value of x to 21. We go to line 3 after that. X is greater than 3 is true, which is the exit condition. When the exit condition is true, you get out of the loop, and then you go to post. Now this is the characteristic of a post-checking loop. You have to perform the action between the repeat until at least once. which is not sometimes desirable. Like in the example that I gave you in the notes, repeat, take a bite until one is full. What if that person just came back from Mitsu and had a big sushi buffet already?
So they don't even want to take the first bite.
You have to take a first bite. According to the logic, you have to take another bite. But I am full, I don't want to take another bite. I'm going to throw up. Take a bite anyway. Okay? Or if you think about channel serving logic, okay? Now how do we do channel serving? We all do that once in a while, except for me because at home my TV is pretty much locked to KVIE. The only station that I watch is KVIE. Well, I mean, the kids like it, and I don't really have any need for any other channels. The internet is out there. If I want to watch the news, if I want to read the news, there are plenty of sources other than the TV. But let's just say that you have, a really nice, package. You are subscribing to cable. You have 600 channels. Okay, you turn on the TV, and then you want to follow the algorithm. The algorithm says, repeat, press the up channel button until you find a channel that you like. Okay, so let's just say that that's the logic that you have to follow. You turn on your TV and go like, oh, I like this station, but you know what? The logic says you have to perform that one step at least once. So you have to press that channel up button. Now, let's just say that out of the 600 channels, only one is what you want. The other 599 channels are not something that you want to watch. Now what do? You have to go through exactly until you get back to that one that you started off with. Then you say, oh, the condition says this is the channel that I like. Then you can get out of the loop. Okay? So are you guys starting to see why sometimes it is not appropriate to perform the action at least once, and then you ask the question, should I do it again? So that's why we have a different kind of loop. Okay, let me save this one first. Save to today's folder. And we'll call this repeat until, because it illustrates how to do repeat until. So let's go ahead and switch to, move on to the next slide. Is this all worthwhile? Because the while is the word that we want to focus on, because this is a while loop. Okay? The while loop is kind of the same as a repeat until, except for two major differences. One, it specifies a condition to stay in the loop instead of to get out of the loop. And two, it checks the condition before the action. So when you look at the picture of a while loop, it looks kind of weird. Okay, it looks like this, because when you come in the first time, you get to the branch first. You don't get to the action first. You get to the branch first. The branch will have a question associated with it. If the answer to the question is false, then you get all the way out of the loop and you continue with the next statement. If the answer to that question is true, then you go in, you perform whatever action is between the while and the end while, and then after the action, what do? You go all the way back to this point here, where you can ask the question again to determine whether it is time to get out or whether you have to perform another step. But the main point is you ask the question first. And that's why in this class, I call this kind of loop a pre-checking loop, because you check the condition before you perform the action. Are we doing okay so far with the concept of a pre-checking loop? So now we can go ahead and test, whether we really understand the behavior of a pre-checking loop using, guess what? A trace. This is the only class where you will have traces. When you move on to other classes, other programming classes, you won't be tracing your algorithms anymore. Because one, the programs will be more complex. It will be very tedious to trace the programs, and two, those professors will assume that you already know the proper behavior of a line in the program. So you don't have to show to your professor that you understand each and every single statement anymore after this class. But in this class, that's our focus. While x is less than 3, do x gets x plus 1 and while. Okay. So basically, it almost looks the same thing, but looks like the same thing, but it is not the same thing. In programming, it is also important to pay attention to little details. In other words, less than and less than or equal to are different things. Your program will work for the most part if you use one or the other, but when you have boundary cases, then it will be wrong. So you have to be very careful when you specify less than versus less than or equal to, that sort of thing. And we'll go ahead and trace this algorithm. In sheet 2, we'll have the first test case. Comments, line number, x, precondition. Let's say in this case, x starts with a value of 1, so I don't have to go through as many iterations. Okay. In this case, we start with line 1. Line 1 is while x is less than 3. We have to evaluate the condition. X is less than 3 is true. Then we go to line
2.
We go to line 2. Very good. Line 2 says we have to add 1 to x and then put the result back into x. X is 1 already. 1 plus 1 is 2. So now x is updated to 2. Then where do we go?
Line 1.
We go back to line 1. Very good. Not post. Okay. It looks a little bit like a conditional statement, because it looks like we have a condition to evaluate, an action to perform. But the difference is when you have a while loop, after you perform the action, you always have to go back to the beginning, which is the while line, in order to re-evaluate the condition. Then you determine whether you have to do it again or not. So in this case, we go back to line 1. We evaluate x is less than 3. Is it true or false?
True.
It's still true because 2 is less than 3. We go back to line 2. X is 2 at this point. 2 plus 1 is 3. And we update x with the value of 3. We go back to line 1. X is less than 3 is false in this case. And we are done. Are we okay with this? Okay. Now let's go for another test case. Okay, this is a slightly more tricky case, but I don't think you guys can be tricked by this. X starts with a value of 20. We start with line 1. Line 1 is asking, x is less than 3 is, it is false to begin with. Where do we go? We go straight to post. Okay. Are there any questions about the pre-checking loop? No questions?
Can you go back to that other one just for a second?
The other test case?
Yeah.
Like this one? Okay. Now, given there are two types of loops, when do we use a pre-checking loop and when do we use a post-checking loop? Well, I can tell you, most of the time, 80 or 90% of the time, it is more appropriate to use a pre-checking loop. Okay, the while loop is more common than the repeat until loop. Okay, because a lot of times you should check the condition before you do even one step in the loop. The only time that you want to use a post-checking loop, let me save this file first, and then I'll go back to the notes to show you under what condition should we use a post-checking loop. Repeat no more. This is one of the very few examples where a post-checking loop makes sense and a pre-checking loop does not. Let's think about this, and this is a program, or this is a part of a program that is interactive with the user. Okay, it is prompting the user and saying, okay, enter a zip code. The user enters a zip code, and the loop says, okay, I'm going to ask for a zip code again if the zip code that you just entered is invalid. So it will keep asking the end user for a zip code as long as that zip code is invalid. It will only get out of the loop when the user enters a valid zip code. Why do you think it makes sense in this case to use a post-checking loop?
You need an input to start with.
Exactly, because the condition that you are checking is the result of the action specified in the loop itself. Are we doing okay so far with this? Okay, because asking for the zip code is the action that is necessary to give you a zip code to check when you evaluate the condition, when you evaluate the until line. That's the only time when a post-checking loop makes more sense than a pre-checking loop. If you think about this, if you turn this into a pre-checking loop, what does it look like? The pre-checking loop will basically say, while the zip code is invalid, ask for a zip code. At first glance, it seems to be correct, but my question is, what is the first zip code that you are checking? You get something, but it is not something that the user inputs, right? So in that case, what if that zip code that you get to begin with to check turn out to be a valid zip code by random, by chance? Then you won't even ask the user to input a zip code, and I think that is not the same as this code anymore. The behavior is no longer the same. Yep.
Could you just ask for the zip code before you hit the while loop?
Yes, you can. You can say and ask for a zip code, and then you can say while the zip code is invalid, ask for a zip code and while. Yes, that would be the same. But then you have two statements of the same thing. You end up with two statements that are both ask for a zip code, because you need one before the loop and you need one in the loop. And that is more cumbersome than this one. But they are equivalent. Yes, the behavior will be equivalent in that case. Are there any questions about loops? Now in C, this is the funny thing, because in C we don't have repeat until. Okay, in C it has do while, which is basically the same thing, except in the case of a do while as compared to repeat until, the condition that you specify is the condition that you need to stay in the loop. Whereas in repeat until, the condition after the until is called the exit condition. You get out when that condition becomes true. Okay? For people who are still having kind of some problem, kind of wrapping your mind around the word while, every time you see while, whether it is do while or while do, doesn't matter. You just say, every time you see a while word, it is the same as long as. It means exactly the same thing as long as. Okay. Are there any questions about loops? Because we are moving fairly fast. We are actually keeping up with my Tuesday and Thursday class. And if you look at the notes, we are now done with loops. The next one is nested statements. We don't really have a lot of time to cover nested statements. So what I'll do is I'm just going to click on this one and show you what it looks like, because you need to read this before the next class so that we can move along just as quickly as today. A nested statement, I'll give you one example here. I'm not going to get into the details because in 5 minutes I cannot explain all the details, so you have to read the notes over this week. This is a nested statement. Now, not only is it a nested statement, if I want to count the number of statements in this code, how many statements are there in this program? Well, let's go ahead and count the simple ones, the assignment statements. We have 1, 2, 3, 4, 5, 6. We have 6 simple assignment statements. But we also have what we call compound statements, okay? Because the while loop is a compound statement. Remember earlier what I said? We have folders and subfolders in pseudocode because of the structured programming approach. So now, this is a statement too. Okay, it is a folder because it has smaller files inside this folder. What is the other folder that we have in this program? The outer while loop. Okay, from line 3 all the way up to line 10 is the other folder. That is the number of statements that we have. So this is one big folder. It has one file inside or 2 files inside and one subfolder. this subfolder has 2 additional files inside it. If you want to look at it from the perspective of a file system and folders and whatnot, that's one way to look at it. And that makes it nested because line 4 is completely inside the outer while loop. Line 5 to line 8, which is the inner loop, is also completely inside the outer loop. Okay? You cannot have a loop that is halfway in a loop and halfway outside of another loop. It has to be completely inside. Okay? So if I want to count the number of statements in this program, it will be 1, 2, 3, 4, 5, 6, 7, 8, and the last one is not, because it's just saying, whatever it's following. So there are how many statements again? I cannot remember.
8.
8, okay. So there are 8 statements in it, but because of the nesting, structure, some statement contains additional statements inside it. Okay. Now the second thing that I want you to think about, you can write it out if you want to, and see if you can, work it out. Is not to have indentations. Okay. So go ahead, type exactly the same program without the indentations, and see if you can follow this code, as quickly or as effectively as the way it is right here with indentation. And then you will start to realize the importance of indentation. Indentation refers to this while here lines up with this and while here. This while here and lines up with this and while here. Okay. That's basically it. That's all that I have for today. So remember to do your homework assignment and read ahead of me. At least finish this particular module if you cannot do any more. And yes, I can check who has been reading the notes.
Can you upload the documents?
Yes, I can. Let me.
Yeah, I tend to get in the way when I try and get out of the car, so I just wait for people.
Upload the notes.
I have a question. I'm
Yes.
on the wait list. I'm trying to see where you going to give ad numbers out this week.
Okay, hold on a second. Let me take a look here. Because I have to count how many people are missing this class. So we got 1. Okay, just saying. Wow, this is not common. Usually I have a lot of people missing the
Yeah.
class. Not this time, because I have, which one is you?
I am right here.
Yeah, see, there are still people ahead of you. So what I can do, I cannot really add you to the class because, the class is already overfilled at this point. So what I can do is I can add you to Moodle, which does not give you a grade at the end of the semester. So you kind of have to keep coming until, people
Yeah, I'm already
actually
on
start to drop.
Moodle. We did that over
Okay.
the week
Okay, that's
last
good.
week.
Okay.
Okay, so
That's
just
good. Yeah, just keep doing it. Just make sure that you attend the class so that on the roll sheet, I still have you show up here.
Yeah.
And just keep doing it. People will start to drop at some point.
Yeah.
Okay. Some people will drop the class. For